We can go down and say draw oval and pass in our oval one. This is going to work just fine, but hopefully you can see that this is bad design. If you have a lot of shapes in your program, this is going to quickly become unmanageable, and you don't want to do something like this. What we want is to be able to only have one method and get the C++ runtime to resolve which one is called at runtime when we get to pass our actual objects, and we will only have one function which is going to take into account hundreds of shapes that we might potentially have in our C++ program. This is going to be much easier to manage, and we will actually be able to achieve this in the next lecture, so stay tuned for that. Another problem with this is if you happen to need to store these shapes in collections. If you need to set up something like this, you will have no choice but to set up different collections for each type. For example, we might set up a collection for circle, a collection for oval, and here we are just using arrays to model our collections. And this is really bad design. If you happen to have 100 shapes in your program, you will set up 100 such collections, and the only difference is that they are just different types. And this is really bad design because even if they are different types, they are related and they are all shapes in our C++ program. And what we really want is to set up one collection which is going to take into account all these kinds of shapes that we might have in our C++ program. And we will be able to achieve this again in the next lecture. But the whole point of this lecture was to show you static binding that we get by default with our inheritance hierarchies. Static binding may be bad if you really are managing a lot of related objects in your C++ program, and all these objects have the same method that each derived class is specializing, but you want the most specialized method to be called on the actual object that you are managing with a base pointer or a base reference. Hopefully this is super clear. I apologize, this lecture turned out to be really long, but I wanted you to make this super clear, and everything else we do in the remainder of this chapter is really going to fall in place. So make sure you understand this, and if you have a problem, do ask me. I will do the best I can to help you out. This is really all I had to share in this lecture. I hope you found it interesting. We are going to stop here in this lecture. In the next one, we're going to show you how you can achieve dynamic binding using virtual functions in C++. Go ahead and finish up here and meet me there. In this lecture, we're going to see how we can achieve dynamic binding or polymorphism using virtual functions in our inheritance hierarchies. In the last lecture, we had a hierarchy like this, where the base class was shape. We had an oval class which was publicly deriving or inheriting from shape, and we had a circle class which was publicly inheriting from oval. And the problem we had was that if we happen to be managing oval or circle objects using shape pointers or shape references, we don't get the correct methods called if we call the draw method on our base pointer or base reference. And this was really bad, and this is something we want in practical C++ programs. I am here to tell you in this lecture that you can just achieve that by doing a tiny modification on your inheritance hierarchy. All you need to do is to mark the methods you need to be dynamically resolved virtual. And we do that by inserting this virtual keyword in front of our function. So we're going to do that on our shape class, we're going to do that on our oval class, and we're going to do that on our circle class. Once we do this, the C++ compiler is going to know I want to be looking at the type of the pointer or reference to know which kind of method to call in my inheritance hierarchy if I happen to be using a base pointer or a base reference to manage a derived object. And we're going to be making this super clear in a minute. And if you are lost, please bear with me, you're going to understand. So let's do this. We're going to modify our shape class and change our draw method to be virtual. As you see here, we're going to head over in our oval class. We're going to modify our draw method and mark it to be virtual using the virtual keyword here. And we're going to move in our circle class and change it to be virtual as you see down here. This is really all we need to do from what we had in the last lecture. And this is going to be magic. Let's look at what we can achieve now. We're going to set up 3 objects: shape, oval, and circle, as you see here. And we're going to be calling our method, which is going to be taking references, and we're going to see that we get the correct, most specific method called. So for example, here we will call the shape draw. Down here we will call the oval draw method because we just passed in an oval object. And on the third line here, we will get the circle draw method called, and we will see it printed out on the console. This is really cool. This is what we want to achieve. If we want to call our methods that take pointers, we can do that. And on the first line here, we will call shape draw. On the second line here, we will call oval draw. And on the third line here, we will call circle draw. This is what we want to achieve. And if we happen to be setting up a row base pointer like we do here and store in a derived object like this, or another way to say this, if we happen to be using this base pointer to manage a derived object and we call the draw method on the base pointer, the compiler is going to know that it will need to resolve this draw method dynamically. The reason is, this is a virtual method, and if a method is virtual, the compiler won't do static binding like we did in the last lecture. The compiler is going to be doing dynamic binding. And with dynamic binding, the compiler is not going to look at the type of the pointer. It is going to look at the type of the actual object that the pointer is managing. And this is going to give us the behavior that we wanted starting from the last lecture. Okay, now that you know this, we're going to head over to Visual Studio Code and play with this a little more. Here we are in our working folder. The current project is polymorphism with virtual functions. We are going to be reusing the code from the last lecture because that's going to give us everything we want. We will leave out the binary file here, which is Rooster, and we're going to copy everything we want. We're going to put that in the current project, and we're going to open this in Visual Studio Code. We are going to have our main CPP file with a bunch of methods here, and we will just need to modify this a little bit to achieve dynamic binding. As we saw in the slides, all we need to do is to mark all these draw methods as virtual. So we're going to say virtual void draw in the shape class. We're going to go in the oval class and do that. We're going to mark our method as virtual. And we are going to go in our circle class and mark our draw method as virtual. Let's do that. And the moment we do this, we're going to get dynamic binding behavior in our inheritance hierarchy here. And this is really cool. So let's go back and try to play with what we had before. I am going to comment out everything we had, and we're going to be doing things in step here. Let's go through the code that uses base pointers because that's where we started out from in the last lecture. And we are going to mark that here. Let's put in some space to make it easy to follow. So we are going to uncomment the line here that calls the draw method when we have a shape object stored in our base pointer, or when we are using a base pointer to manage a shape object here. We can also comment out all these lines because we don't want this to do anything. And let's see. Yes, this is what we want. We are setting up our shapes, and we are using a base pointer to manage an actual shape object. And if we call the draw method, we expect this to call shape draw. And this is what we're going to get. Let's build our program. We're going to pass this through GCC, our favorite compiler. The build is going to be good. We can bring up a PowerShell window we can use to play with us. If we call Rooster, we're going to see that shape draw is called, and we are drawing shape 1. Now, if we change this to manage an actual oval object, we can do that. We can do that through this line here, and we expect this to call oval draw. And because the draw method is now virtual, this will use dynamic binding. Again, with dynamic binding, we are telling the compiler, don't look at the type of the base pointer, look at the type of the actual object that the pointer is managing. And the compiler is going to see that this object is an oval object, and it will call the oval version of the draw method here. And this is really cool. This is what we want. Let's run the task to build with GCC again. The build is going to be good. As you see here, we can clear. And if we run Rooster, look at this. Oval draw called, and we are going to be drawing our oval object. And this is the data we have inside. We can use this radius data to draw this on the screen if that's what we are after in our C++ program. And this is really cool. We can even use our base pointer to manage a circle object. We can do that. And if we do that and call the draw method, because this draw method is now virtual, the compiler will note that it doesn't need to look at the type of the pointer that we are using to manage our object. The compiler is going to look at the type of the actual object that the base pointer is managing. And in this case, it happens to be a circle object. So here we will call circle draw, and this is going to draw our circle on the screen. And this is really going to be super cool. So let's pass this through GCC, and we're going to see this in action. The build is going to be good. We can clear and run Rooster, and you see that we are drawing a circle. And this is really cool. And just using virtual functions, we can really achieve powerful features. And you see that this wasn't really hard to achieve. All we had to do was to mark our inherited methods as virtual. And this is going to tell the compiler to do dynamic binding. And this is going to be super cool. Let's see that we can also achieve the same thing using base references. I am not going to run the code where we are using a base reference. I am not going to be running the code where we are using a base reference to manage a base object, because that's going to be really boring. But what we can do is put in an oval object. For example, we can say oval1 and say shape ref and call the draw method. Again, this is dynamic binding because the draw method is virtual, so the compiler is not going to look at the type of the reference to decide which version of the draw method to call. It is going to look at the actual object that this reference is managing. And it is going to see that the type of the object is oval. So C++ is going to call the oval version of the draw method. That's what we're going to get if we run this program here. Let's build and see this. We're going to pass this through GCC. The build should be good. As we see here, we are going to clear and run Rooster. You see, we are drawing oval. If we happen to be using this to manage our circle object, let's do that. We will see that we will get the circle method called. Okay, let's build, and we're going to pass this through GCC to do that. The build is going to be good. We can clear and run Rooster. You see that we are drawing a circle because our base pointer is now managing a circle object. Now, because we are using dynamic binding or late binding, as some people call it, we can really do all kinds of crazy things. The first thing we can achieve is set up one single method, which is really going to draw any kind of shape we throw at it. So let's do something like this. We're going to say void, and we're going to say draw shape, and it is going to take a shape pointer, let's say S. And the only thing we're going to do in this function is say sDraw. This is going to call the draw method on whatever parameter that we pass in here. And watch this. If we go down here and uncomment this section on drawing shapes, if we say draw and pass in a circle, for example, or let's pass in oval and do this one level and do this level by level, we're going to pass in oval 1, and we should pass an address because this is taking a pointer. So let's do this. And if we build and run this program, let's see what happens here. We're going to build with GCC. The build is going to be good, as you see here. If we clear and run Rooster, you see, and let's take out this thing using base references here, because this is just going to confuse us. We're going to build again and use GCC for this. The build is going to be good. We can clear and run Rooster. You see, oval draw, because we are passing in a novel object. If we pass in our shape, let's say shape 1, for example, we're going to build. The build is going to be good, as you see here. If we clear and run Rooster, we're going to see shape draw. If we pass in circle, let's do that. And build again, we're going to build with GCC. We're going to clear and run Rooster. You're going to see that circle draw is called, and this is really cool. We can only use a single method, and this method is going to take any shape we throw at it, and it is going to draw it. If we happen to be having 100 kinds of shapes in our program, we can just, for example, loop through a collection containing those shapes And if we call the draw method on any shape we store in our collection, we're going to get the correct shape drawn, and this is super cool. This is really powerful, and I hope you are excited to be able to achieve this in C++. Now, we can also achieve the same thing by using a method that takes a reference, for example. So we can say void draw shape, let's say v1, and we're going to pass a reference. We can say const and pass a reference and say SR to say shape reference. We can do that. And we're going to say sDraw. We're going to call the draw method on this reference. And let's see what happens if we try this out. Let's say SR. That's what we should say here. And this is going to be taken by our Visual Studio Code editor. If we go in here and change this to say draw shape v1, we can pass in shape 1. We can do that because this is taking a reference now. If we build with GCC, we are going to see that the build is good. We can clear. Let's clear. We're going to run Rooster. This is going to call shape draw because we are using a reference to manage a shape object. We can also pass in over1, and we're going to build again and see how this works. The build is going to be good. We can clear and run Rooster. We're going to say over draw, and we're going to see our information here. If we pass in our circle object and build, we're going to pass this through GCC. The build is going to be good. We can clear and run Rooster. This is going to draw a circle for us. And this is really cool. We have one method again that is taking a parameter by reference, but we can use this method to draw any kind of shape in our inheritance hierarchy. This is going to work really well, and it is doing dynamic binding, which is powered by virtual functions we are using in our inheritance hierarchy here. You should really keep this in mind. Now, let's go back and see if we can even use row pointers to do stuff. I am going to comment this out, and I am going to say row pointers, because I want you to see something. We're going to set up a shape pointer. We're going to say shape PTR. Do we have that on top here? Let's see if we do. Yes, we have shape PTR. So let's say shape PTR and pass it an oval object. We're going to pass an oval again, and we're going to pass the address of oval1. This is going to do. We can call the draw method and get it called polymorphically, or get it called using dynamic binding. We can say shape PTR and say draw. This is going to call the correct version. But one thing I want you to see is that if a method is not polymorphic, or if a method is not virtual, you won't get it called using polymorphism. For example, if we go to our oval class, we're going to see that we have a bunch of getters. Let's go in and make them public so that they are callable from the outside. And if we try and get this called polymorphically or using dynamic binding, that's not going to work. Let's do that. We're going to say get xrad. And the reason we might want to do something like this is because we have this method here, and it is set up on our oval class. So because we are using a base pointer to manage an oval object, some of you might think, I might be able to call this method because I am able to call the draw method, which is also in the public scope of our oval class. But that's not going to work because this method here is not virtual. Dynamic binding or polymorphism is only going to work if your methods are virtual and they are set up across your inheritance hierarchy. So this is not going to work if you try to do something like this. This is going to give you a compiler error. Let's try and build and see the compiler error, and we're going to see an error that says that no such method on this object. Let's go here. Class shape has no member named getXrad. Because the method is not virtual, the compiler is going to do static binding, and it is going to be using the type of the pointer, which is shape, to resolve this method. And it is going to see that in shape, we don't have a method called getXrad, and the compiler is going to throw this compiler error here. This is what we get. So this is not going to work, and I want you to be aware of this. Another thing I want you to see is that because we are using dynamic binding now, we don't need to set up all kinds of crazy collections to take into account different shapes that we have in our C++ program. What we're going to do here is use a base pointer to manage the data that we store in our array here. So all I am going to do is remove all this dirt here, because this is really dirt. You don't want to do something like that. And we're going to use a base pointer, which is a shape pointer, and use that to set up an array which can handle any kind of shape we have in our inheritance hierarchy. So we can store in shape objects, we can store in oval objects, we can store in circle objects. And if we look like we do here, we're going to get the correct method called, and this is going to be super cool. So let's try and run this program. We're going to pass this through GCC. Why do we have the red thing here? Let's build and see if it goes away. Maybe this is Visual Studio Code having a problem with our code. The build is good, so Visual Studio Code was playing with us. We're going to clear and run Rooster. You're going to see that we're going to be looping through this array here. And on the first iteration, we're going to call shape draw because the first thing is a shape. On the second iteration, we're going to call oval draw because the second thing is an oval. And we're going to hit the third iteration and call circle draw because the third thing in this collection is a circle. Hopefully you can see that this is going to simplify our programs a lot compared to what we were able to do in the last lecture. And this is really all I had to share in this lecture, showing you that you can achieve dynamic binding or polymorphism or late binding, as some people call it, using virtual functions in your inheritance hierarchy. Again, all we had to do was mark our member functions as virtual, and the compiler is going to know that it can set up dynamic polymorphism for your types if you happen to be managing them using a base pointer or a base reference. We are going to stop here in this lecture. In the next one, we're going to learn about slicing and the size of polymorphic objects. Go ahead and finish up here and meet me there. In this lecture, we're going to explore the size of polymorphic objects, or objects that use dynamic binding, and we're going to learn about the concept of slicing if you happen to assign a derived object to a base object. We're going to see how this works out. In the last two lectures, we saw that we could achieve static binding using a setup like this. We can set up an inheritance hierarchy, and we're going to have oval derive or inherit from shape, and we're going to have circle inherit or derive from oval here. And our methods are going to be raw, they are not going to be virtual on anything, and this is going to do static binding. If you happen to manage a derived object through a base pointer or reference, you won't get dynamic calls. You will get static binding, and the compiler will use the base pointer or base reference to decide which draw method to call on your object. We also saw that we could achieve dynamic binding using virtual functions, and all we needed to do was mark our methods as virtual in our inheritance hierarchy here, and this would give us polymorphism or dynamic binding. But one thing you should know is that dynamic binding is not free. You're going to be paying in terms of memory to get all these cool things we saw in the last lecture. And we're going to be proving that in this lecture. What we're going to be doing is basically set up our inheritance hierarchy, and we are going to set that up in such a way that it is going to be using static binding. We're going to see the sizes we get printed out here, and we're going to use dynamic binding and compare these sizes. And the constatation is going to be that with dynamic binding, your objects are going to be much larger because your C++ program will need to keep track of the information that allows it to resolve function calls dynamically. And that information is stored in what we call virtual tables, but I am not going to go into that here because it is really out of scope of a course like this. But I want you to be aware of this. If you use dynamic binding, your objects are going to be much larger. Okay, the first thing I want to bring your attention to is object slicing. And we're going to look at a simple example here. We have our objects, we have a shape object, we have an oval object, and we have a circle object. And down here, we want to assign our circle object to a shape object. Now, notice that here we are not using a pointer or a reference. These are just raw objects that we are assigning to each other. And what the compiler is basically going to do, it's going to notice that a circle has a shape poured into it. And it is going to strip off the outer layers, or in other words, it is going to strip off the circle layer, it is going to strip off the oval layer, and it is going to leave in the shape part, and that's what it is going to assign to our shape object here. Let's visualize this. Our shape class looks like what we have here on the left. Our oval class has a shape part into it, and our circle is going to have an oval part into it, and that oval part is going to have a shape part of it, and this is the setup that we have here. Now, if we do our assignment, we're going to do something like this. The compiler is going to see that we are really assigning a circle to a shape, and the compiler is going to notice that what we have on the left is just a shape, and we don't have enough space to store information about oval and circle here. So what the compiler is going to do, it is going to strip off all these things that we don't really need, and it is going to leave in only the shape part that we can assign on what we have to the left. So it is going to strip off all these things, and we are going to be left with something like this. And then what we have on the right is going to be assigned on the left, and we will have our data stored in our shape2 object. And if we try to use it, that's what you're going to get in memory. So this is referred to as slicing. Again, the compiler is going to notice that it doesn't really have enough space on the left to store everything we have to the right of the assignment here, and it is going to strip off or slice off everything we don't need, and it is only going to leave in the shape part, and that's what it is going to assign on our object that we have on the left of the assignment operator here. And this is referred to as slicing in C++ terminology. I just want you to be aware of this, and we're going to see a lot of this starting from now. Now that you know this, we're going to head over to Visual Studio Code and play with this a little more. Here we are in our working folder. The current project is size of polymorphic objects and slicing. We are going to grab the code from the last lecture, so let's grab everything except for the binary file. We are going to copy everything and we're going to put that in the current folder. And we're going to open this little guy in Visual Studio Code by dragging and dropping here. This is going to give us our project, and we can head over in the main CPP file and clean up all the mess we got from the last previous lectures. We can also take out these functions because I don't think we need them here. And we are going to check out on our classes. Notice that we are using dynamic polymorphism because we have virtual functions here. So if we happen to be using base pointers or base references to manage our derived objects, we will get polymorphic results. Okay, the first thing we want to see is the size of objects for our classes here because we are using virtual functions. Let's head over in the main CPP file, and we're going to put in a piece of code which is just going to use the size of operator to print the sizes of objects of these classes. We can try to build and run this program. We're going to use GCC here. The build is just going to be good. We can bring up a PowerShell window we can use to run these programs. We're going to do that. New terminal. This is going to bring us our window here. We can clear and run Rooster. We're going to get 40, 56, and 56. So you see that these are our sizes. So let's say that with dynamic is going to be 40 for the base class. With dynamic polymorphism, we're going to get 56 for the oval object, and we're going to get dynamic 56 for the circle object here. Now, we're going to remove the setup that uses polymorphism, and we're going to see the results that we get. All we need to do is to remove the virtual keyword here. We can comment it out. We can do something like this in shape, and we're going to hop over in oval and comment out the virtual keyword. We can do something like this, and this is going to work without removing this completely from our code because we still need to leave this in as a reference. We're going to hop over to circle and do the same thing. And now that we have this set up, we can hop over to our main CPP file. We're going to see that we don't have any squiggly lines of some kind, so this is going to be accepted by the compiler. But if we build and run this program, we're going to see different sizes. Let's see if the build is good. It is good, as you see here. We can clear and run Rooster. Now you see that with static binding, the base object is 32 bytes. The oval object is going to be 48. And hopefully you can see that with dynamic polymorphism, our objects are going to be much larger because the compiler has to keep track of the information that allows it to dynamically resolve virtual function calls. That's why our objects are larger with polymorphism. And you should know that you are not getting polymorphic results for free. You are going to be paying in terms of much more memory that you use for your objects in your C++ programs. This is the first thing I want you to see in this lecture. The second thing I want you to be aware of is the concept of slicing. And this is going to happen if you happen to take a row derived object and assign that to a row-based object. Let's do something like that. We are going to create a circle object, and then we're going to say shape, and say shape here. And we're going to say equals circle1. This is something we could do, but notice that the compiler is not giving us any kind of compiler error because we can assign a circle to a shape because a circle is really a shape. But from what we know in our inheritance hierarchy, a circle is really much more than a row shape. A circle has oval information in it, and it also has circle information in it. So it is really much larger and much wider than a shape object. But the compiler is going to see that we are trying to assign a circle to a shape, and it is going to be smart enough to know that we don't really need oval and circle information in our shape object that we are storing here. So the compiler is going to slice off circle and oval information, and it is going to leave in shape information, and that's the only thing we will be able to use with this shape variable that we have in our C++ program. So if we say shape draw, you can try to guess what we are going to get. And let's go back and re-enable polymorphism, because some of you might think we are going to get polymorphic results with this setup here. That's not what we're going to get because we are not going through base references or base pointers to do what we are doing in this example on slicing here. So because we are not using base references or base pointers in this line here, the compiler is going to see that these are row objects, and it is going to do slicing and slice off things we don't need in our shape variable that we are setting up on line 16 here. So if we call the draw method, this is going to call shape draw. It is not going to do dynamic polymorphism here. You should be aware of this. If you're not using base pointers or references and you hope to get dynamic polymorphism results, I hate to break it to you, but you're going to be disappointed because the compiler is going to slice off derived class information, and all you're going to be left with is base class information here. That's why this is going to call shape draw. Let's build and run and really make you see this. This is going to go through GCC, our favorite compiler. The build is going to be good. We can clear and run Rooster. You're going to see that it is going to say shape draw. Even if we tried to assign a circle to a shape here, this is going to disappoint us because this is really going to slice off circle and oval information, and it is just going to leave in the shape nucleus that we have in our circle object here, if I can say it like that. This is really all I had to share in this lecture. I hope you found it interesting. We are going to stop here in this lecture. In the next one, we're going to see what happens if we try to store polymorphic objects in collections. Go ahead and finish up here and meet me there. In this lecture, we're going to explore what happens if you try to directly store polymorphic objects in a collection like an array. In the last lecture, we have seen that if you assign a derived object to a base object, the data from the derived object is going to be basically sliced off. If you assign an oval to a shape, the oval part of the object is going to be sliced off, and we're going to be left with only shape data that we assign to our shape object. We saw that this was referred to as slicing in C++, and the same is going to happen if you assign a circle object to a shape. The circle information is going to be sliced off, then the oval information is also going to be sliced off, and we're going to be left with the inner shape part that we assign to our shape object here. Now, I want you to see that this can happen indirectly in ways that you might not expect. And we are going to use our inheritance hierarchy again. The base class is going to be shape. We're going to inherit from that and get oval, and we're going to inherit from oval and get our circle class here. So let's look at a piece of code. Here we are creating a bunch of objects. We have a bunch of circles and ovals, and we are setting up an array that is going to directly store shape objects. But what we are doing is storing our pre-created objects in our array here. And from what you already know, if you store objects in an array like this, this is going to create copies even if you can't see that directly. So what we have in our array here is not any kind of direct reference to the object we have on top here. These are just copies. And notice what is happening. We are copying derived objects in spots that are designed to store direct shape objects. And you might guess what this is going to do. This is going to slice off circle and oval information, and only shape information is going to be stored in this array here. So if we happen to loop through this array like we do here and try to call the draw method, this is not going to call the most specific draw method for circle or oval. This is just going to call the shape version of our draw method here. This is something I want you to see. Okay, some of you might say, what if I take my shape information in here and assign that to a pointer and then go through that pointer to call the draw method? Well, I hate to break it to you, but the moment your data is sliced off in a situation like this, you'll never get that data back. So even if you try and take the object and assign that to a pointer or a reference, you're never going to get polymorphic data again. The data has been lost permanently and you never get that. So even if you try to go through a pointer or a reference to manage your object that we have in this array, if we call the draw method, we won't get polymorphic behavior. We will get the shape version of our draw method called. So the data has been sliced off permanently if we store our derived objects in an array like this, or even if we directly assign a derived object to a base object. This is going to slice off the data and we will never get it back anyway. You should really know this. Okay, anytime I try to explain this, students mostly come up with this question. What if I try to store references in my array and do something like this? Now, this is not going to work, and this is not even go past the compilation stage of your program. The reason is we can't store references in a collection. And the reason has to do with the left assignability rule. You can't assign to a reference and change the reference to store somewhere else. And to really drive this home, let's look at this example here. We have a variable called a, it is of int type, and we have a 56 value inside. And we set up a reference which is going to be referencing the data we have in a. And down on this line here, we try to change the data in our reference, but this is not going to be changing where this reference is pointing to or where this reference is referencing. This will merely be changing the values in our reference here. And once we have this reference, we'll never be able to change where it is pointing again. So from this, hopefully you can understand that references are not left assignable. You can't store things that are not left assignable in an array because an array is designed to modify the data of what is stored inside. So if we set up an array like this, the compiler thinks that at some later point you will want to assign other data to what is already stored in this array. And there is a hard requirement on the data you store in your collections for the type of that data at least to be left assignable, and references are not left assignable, so we can't store them in a collection like this. If we're trying to do this, we're going to get a compiler error. But again, some of you are going to say, what if we store in pointers? Well, this is going to work. This is the basic working principle of polymorphism, going through base pointers to manage derived objects. This is going to use polymorphism, and here we will get the most basic draw method called. So if our object is a circle, we will call the draw method on the circle object. If it is an oval, we're going to call the draw method for the oval part of our object here. This is even going to work if we go through smart pointers. So if we do something like this and store in smart pointers and create our smart pointers on the fly in our initializer here, this is going to work because really a smart pointer is a wrapper on top of a regular row pointer in C++. So again, the message here is that you need to be careful on what you store in your collections. If it is a raw piece of data, your data is going to be sliced off if you store derived objects in a collection that is designed to store base class data. If you store in references, that's not even going to compile. But if you store in any kind of pointer, raw or smart, this is going to work because polymorphism was designed in the first place to work with base pointers that are managing derived objects. And this is really cool, and I want you to be aware of this. Now that you know this, we're going to head over to Visual Studio Code and play with this a little more. Here we are in our working folder. The current project is polymorphic objects stored in collections. We are going to reuse the code from the last lecture because we need our inheritance hierarchy here. And this is going to serve us just well. We're going to copy this. And we are going to head over in our current project and put in our code. And then we're going to open this in Visual Studio Code pretty quick. Let's do this. This is going to give us our code, and we have our shape class, which is really what we already know. We have our oval class and we have our circle class. Take a good look at this. And what we want to see is what happens if we use different kinds of setups to store objects of this inheritance hierarchy in a collection like an array. Let's go back to our main CPP file, and we are going to take out what we have in here. We're going to set up what we're going to be using in this lecture. We are going to set up a bunch of objects that we're going to be using here, basically a bunch of circles and ovals. We can close the left sidebar here and have some more breathing room. After this, we're going to set up an array which is going to store copies of this object in this array here, which is called shapes1. And after this, we're going to try and loop through this array and try to do things with it. For example, we can say for shape, and we may want to call the draw method on our copy here. So for example, we can say s and say draw. We're going to see what happens here. And let's say references because we don't want copies in our range-based for loop here. So this is going to avoid copies we do in this loop. And we're going to be directly referencing whatever we have in this array here. Now, what do you expect to get? We have derived objects in this array, and with the setup we have here, because we are using virtual functions, one would expect to get polymorphic behavior. So here we would expect to get the draw versions in circle and oval to be called, but that's not what is going to happen. We're going to see that we're going to be calling shape versions of our draw methods. Let's try and build and show you this. We're going to build with GCC, our favorite compiler. The build is going to go through. We can kill this and bring up a PowerShell window to allow us to run our program. We're going to say rooster here, and you're going to see that we are drawing circle 1, oval 1, circle 2, oval 2, circle 3, oval 3, but we are calling the shape versions of our draw method. And the reason is we are slicing off derived class information in our objects the moment we try to make a copy, and copy in a spot that is designed to store objects of the base class. So this is basically what we saw in the last lecture. on slicing, but it is disguised because we are storing data in an array. And when you store data in an array like this, you're going to be making copies and storing copies in your array. And in any copy you make, you're going to be basically slicing off oval and circle information and only storing in shape information for our objects here. This is what the compiler is going to do. And to really try and prove this, we can try and print the size of these objects and see the sizes of these objects in this array here when we loop. So for example, we can say stdc out size of circle1. Do we have circle1? Yes, we do. So we're going to say size of circle1 here, and we're going to put its size information out here to be seen by everybody. We're going to say size of circle1, and we're going to print it out. And we are also going to print the size of whatever iteration we are at in our loop here. That's the first thing we're going to print, and we're going to say size of object, and we're going to say size of s. This is going to do. And we're going to loop and see if the information we have on the outside is the same as we have on the outside. Again, we are printing this information on the direct object, which is really not yet in our array. And in fact, we can bring this in front of our array to make this super clear. And in our loop, we are printing information on a copy that we have in our array, because this is the real deal we have in our array, because this is a reference. Hopefully this is going to make sense and prove to you that we are going to be working with derived objects, and that the data is going to be sliced off if we copy the data in our array here. This is what I want you to see. So we're going to run this again. We're going to pass this through GCC. The build is going to be good. We can clear and run Rooster. Now, let's look at what we have here. Size of circle1 is 56, but you're going to see that the size for all our objects in our array has shrunk to 40 because derived class information has been sliced off the moment we copied our data in our array here. And this is what I want you to see. And I think we can even see this if we go through our debugger. For example, we can put a breakpoint here and open our run tab. And if we try to run our program through the debugger, the build is going to be good. And the binary is going to be passed into our debugger. And we're going to hit our breakpoint in a minute. So let's wait for this. And we have hit our breakpoint here. But what we can do now is look at our local variables on the left. Let's look at our array. The array is called shapes. And if we go up, we're going to see our shapes1 array. And we're going to see that we have 5 indexes here because we have 6 elements inside. We can expand and see what we have at index 0. And you're going to see that we just have description data because this is a shape. If we go back in our class, we're going to see that the only thing we have in our shape class is really a description member variable. And it is what we see in our array here, just description information, because this is a shape object and we have lost or derived class information. And this is really cool. But if we go on top and, for example, expand circle1, we're going to see that we have a novel part of us and we have a shape part of us. But these things have been stripped off in our array when we slice off the data from derived objects to only store shape information in our array here. I hope this makes sense now. We're going to kill our debugging session because we don't need this anymore. And we are going to comment this out and see some other things. So we are going to comment with our data here. We're going to say, if you store row derived objects in an array, which was set up to store base class object, the data is going to be sliced off. This is something I want you to know. But some of you are going to say, what if we store in references? Okay, so let's try and do that. We're going to set up a piece of code like this, and we're going to set up an array called shapes2. And this array is going to be basically storing references to the objects we have on top here. And we're going to see what happens. You notice that we have a squiggly line already. And this is saying this is not going to work because references can't really be stored in collections. Again, as we saw in the slides, the reason is because references are not left assignable and they can't be stored in a collection like an array here. The basic requirement on the types that you can store in your array is that they have to be left assignable, and our references are not left assignable, so this is not going to compile. If we try to build our program, we're going to see that we're going to get weird compiler errors, and the build is going to finish with errors. And if we go up, we're going to see that declaration of shapes to as array of references, and this is not allowed. You can't have an array of references in C++, and this is the reason why. So we're going to get a compiler error here. Okay, so now you know this, but some of you are going to say, what if we go through pointers? Well, that's going to work because polymorphism through virtual functions was basically designed to work with base pointers that are managing derived objects. And this is what we have here. So if we look, we're going to be getting polymorphic behavior. And if we call our draw method on our pointer here, we're going to get the most specific draw method called, and this is what we want. So we're going to try and build this again and show you that this is going to work. The build is going to be good. We can clear and run Rooster. And we're going to see that we are going to be looping around. And if we call the draw method, we're going to call the oval draw method, circle draw method, oval draw method, circle draw method. This is basically what we want. And we are going through base pointers to really use polymorphism here. This is even going to work if you go through smart pointers. So let's comment this out and set up another example to really drive this home. You can really use any kind of smart pointer. You can use unique pointer or shared pointers. So here we will just be storing in shared pointers because this is easier to handle. And we're going to head over to the top and include the memory header. If you remember, if you want to use smart pointers in C++, you will have to include the memory header, which brings in the data to set up smart pointers in your C++ code. So this is going to look good now. And if we build, we're going to get the most specific version of our draw method called through polymorphism that is using virtual functions here. So let's build and show you that this is going to work. The build is going to be good. We can clear and run Rooster, and we are going to get our versions of draw called, the version for circle and the version for oval, because we are using base pointers to manage derived objects here. And our class inheritance hierarchy is using virtual functions for the draw method here. So this is going to work. This is really all I wanted you to see in this lecture. You should be careful if you try to store derived objects in an array that was designed to store base class data. If you are using raw data, you're going to get slicing, and you really need to be aware of this because you want to have derived class information. If you try to store in references, this is not even going to compile because references are not left assignable. But this is going to work if you use raw pointers or smart pointers, because polymorphism was basically designed to work with base pointers or references that are managing a derived object, which uses polymorphism. We are going to stop here in this lecture. In the next one, we're going to learn about the override mechanism in C++. Go ahead and finish up here and meet me there. In this lecture, we're going to learn about the override specification, a kind of setup you can do to avoid errors in your inheritance hierarchies if you use virtual functions to set up polymorphic behavior for your derived objects. And this is something that was set up in C++ to avoid easy to make mistakes. For example, if you have an inheritance hierarchy like this, you might be meaning to set up a draw overrides for what we have in the base class. And an override is really a most specific method that you have in your derived class to really hide what we had in the base class. For example, the draw method in oval is going to be overriding or hiding what we have in shape. And the draw method in circle is going to be overriding or hiding what we have in oval. This is the idea here. But as you set up your overrides, you might make mistakes. For example, you may mean to say draw and use a W that is in uppercase, and that's going to be bad because what you will be putting in oval is going to be a completely separate method that is different from what we have on the top, and this is going to be really bad. You're not going to get polymorphic behavior for the draw method in oval because we are simply not overriding the draw method from shape, and this is going to be bad. So in C++, we can avoid these problems by explicitly specifying that the draw method we have in oval is an override, and we can add this specification after our method header. And the C++ compiler is going to enforce that we are actually overriding a method that exists in our parent class, which happens to be shape here. If we have no method called draw in the base class, we're going to get a compiler error because we won't be basically overriding any method here. This is going to protect us from problems if we make typos in setting up our polymorphic methods here. This is the main thing we can achieve with the override specification. Now that you know this, we're going to head over to Visual Studio Code and play with this a little more. Here we are in our working folder. The current project is override here. We're going to grab the code from the last lecture because we are basically going to be reusing the same code over and over, building on top of that if we need to do that. So we're going to put in our code, and we are going to open this in Visual Studio Code by dragging and dropping here. This is going to give us our code, and we can really do whatever we want with it. I think we can leave in the code that is using the base pointer to manage our derived objects. I think this is going to serve us well enough, and we can take out everything else because that's just going to be confusion. We don't need all this here. This is going to be serving us well. Now, we want to learn about the override keyword. And to learn about that, we're going to introduce a typo on purpose here. For example, suppose we want to set up a draw override and we use an uppercase letter here for the W keyword. I don't think this is really easy to spot once you've made this mistake, and you're not going to be getting any compiler error because this is something valid. You can set up a completely new method and call it draw, and this is going to work, but this will be very hard to spot in your program, and the compiler won't protect you, as we just said. If we build our program, you're going to see that it is going to build just fine. So let's pass this through GCC. The build is going to be good, but we want to get the behavior that we want. I think we can take out this stdc out statement inside our for loop here, and we can build again. This is going to be less confusing. Okay, so the build is good. We can bring up our PowerShell window, and we're going to run Rooster and see what happens. You're going to see that for circle, we're going to draw a circle, but for oval, we're going to be drawing shape. So what is happening here? We are overriding our draw method in the oval class, so we should get polymorphic behavior because this is a virtual function and it is called draw, exactly the same thing like we had in the base class, except we've made a really simple typo here, but it is really hard to track and get hold of. We have named our method draw, but the W is in uppercase. So this is a completely different method than the draw method we originally intended to override in our base class. And this is really hard to follow and keep track of. We can protect ourselves by adding the override specification. So if we say override, the compiler is going to help out and make sure that we are actually trying to override a method that exists in the shape class. And if it doesn't exist, we're going to get a compiler error. Then we're going to look at this and really spot this mistake here. This is what you can achieve with the override keyword. And in fact, I do recommend and advise you to use this in your inheritance hierarchy if you happen to be using virtual functions, because this is going to save you a lot of time if you make mistakes like this. So we're going to try and run this and show you the compiler error we get. So let's do that. We're going to pass this through GCC. The build is going to fail as we see here, and we're going to get a compiler error saying error virtual void overall draw const marked override but does not override. This is super clear. We are saying we want to override here, but we're not overriding any method called draw with an uppercase because we don't have that in shape here. This is the message. Once we see the problem, we can correct it. We're going to use a lowercase letter for W, and this is going to work just fine. Now, we're going to use the same mechanism to protect ourselves from ourselves in Circle class. So we're going to override our draw method, but we're going to say that we want to override explicitly. And if we build now, let's pass this through GCC. This is going to build successfully, and if we run our program, we're going to get polymorphic behavior. Let's do that. You see that circle draw, overdraw, circle draw, overdraw. This is what we expect. This is really cool. This is really all I had to share in this lecture. I hope you found it interesting. Use the override keyword in your inheritance hierarchy because that's going to protect you from easy to make typos that are really going to give you a hard time otherwise. We are going to stop here in this lecture. In the next one, we're going to explore the concepts of overriding and hiding in detail. Go ahead and finish up here and meet me there. In this lecture, we're going to zoom in on overloading, overriding, and hiding. We have seen that overriding is a mechanism we have in C++ to be able to set up most specific versions of our virtual methods in derived classes. So for example, the draw method we have in oval is overriding or eclipsing the one we have in shape, and the draw method in circle is overriding or hiding or eclipsing the one we have in oval. This is the concept here. But what happens if we introduce the concept of overloading and mix that up with overriding as we have seen so far? So suppose we do something like this. This is our shape class. It is going to have two versions of the draw method. We have one that takes one parameter. For example, this could be the color that we want to draw our shape with. And another one is not going to take any parameter. And these are two overloads of our virtual method here. So what is going to happen in our derived classes that are going to inherit this virtual method? So let's look at an example. Here we have a simple example that is setting up objects of our shapes. We have a shape object, we have an oval object, and we have a circle object here. If we call the draw method on our most derived class, which is circle, we're going to see that this is going to work. We can draw without a parameter, and we can draw with one parameter, which is going to be our color depth. This is going to work just fine. We will be reusing our inherited method from the shape class, and this is really cool. But what happens if you override this method in our oval class? Suppose we hijack the inheriting process and set up another draw method in our oval class, and we only override the overload that doesn't take any parameter. We can do something like this. But the moment you do this, this is going to only override this method, and it is going to hide all the other draw methods that we had in our base class, which is shape here. And this is something I want you to know. So once you override a single overload of your virtual functions, all the other overloads are going to be hidden, and they won't be usable anymore by downstream inheriting classes. If you want all the overloads to be available to downstream inheriting classes, you have no choice but to explicitly override each of them, and that's how it's going to work. So if we look at the example here, we're going to see that the draw call without a parameter is going to work because this is overridden in our oval class. But if we call the one which takes a parameter, this is going to be hidden at the oval level, and we won't have access to that in circle. And if we're trying to call this, we're going to get a compiler error. Again, the message is, if you override one overload of your virtual functions in the base class, all the other ones are going to be hidden, and you have no choice but to explicitly override them for them to be available and usable in downstream classes. This is the message I want to convey here. Okay, so now we know this, but what if we set up another overload downstream? For example, what if we go in our oval class and set up another overload, which is going to have two parameters? For example, we might have the color depth and the color here that we want to draw with. Okay, so one thing you should know is that this method is not going to participate in shape polymorphism. And what I mean is that if we go through a base pointer or reference to manage derived objects, we can't really call this method with shape polymorphism. So if we go through our shape pointer or reference, we want to be really able to call this method. If we try to call it, we will get a compiler error. The reason is this method is not known to the shape class. That's why it's not going to participate in shape polymorphism. The only methods that are going to participate in shape polymorphism are the methods that are declared in the base class, and they are virtual. This is the condition here. And if you violate this condition in any way, shape polymorphism or base class polymorphism in this case is not going to work, and you will get a compiler error. So if you try to do something like this and you want to call your draw method with 2 parameters, you're going to get a bunch of compiler errors, and this is not going to work. Another thing I want you to see is that if you assign a derived object to a base object, your derived virtual functions are going to be wiped out as part of the slicing that we have learned about already. So the circle part is going to be wiped out, the oval part is going to be sliced off, and the draw method is going to go with our oval part, and we will only be left with the shape part. And if we try to call this method here, we will get a compiler error because it's no longer available, it's been sliced off. This is really what I want you to see here. Now that we know this, we're going to head over to Visual Studio Code and play with this a little more. Here we are in our working folder. The current project is overloading, overriding, and hiding. We want to explore these concepts in a little more detail. We're going to grab the code from the last lecture because that's going to be a good starting point. We're going to take out the binary. We don't want that, and we're going to copy. And we're going to put that in our current project here. This is going to do. And we are going to open this in Visual Studio Code pretty quick by dragging and dropping here. And we're going to see that we have a bunch of virtual functions here. We just have the draw version, but we can set up an overload of this draw method here. This is what we want to do. So I am going to go below here and set up an overload of this method. This is going to be taking the color depth as a parameter, and we want to see how usable this is downstream. So we're going to go down in the main CPP function and take out what we don't need here. We really need a bunch of objects. We can set up circle 1 and oval 1, and we will see that we can call these methods. We're going to say circle 1 draw without a parameter, and we're going to say circle 1 draw and pass in 44 as our parameter. And let's go back and make sure that we have our overload n. This is going to be taking the color depth. And let's try and build our program because we have a squiggly line here. Let's see if it is just Visual Studio Code playing games with us. We're going to pass this through GCC, and we will have a compiler error here. So what is going on? Candidate virtual draw const. Let's go up and see what kind of problem we have here. This is the concept we just talked about in the slides. We are setting up our overloads here, but this is being eclipsed by the overloads that we are setting up in oval. You see we have a draw override, and this is also being eclipsed by the override we have in our circle class here. If we want the 2 overloads we have from shape to be available, we can comment out the overrides we have both in circle and oval. Let's do that. And that's going to be available and usable. So let's do that. This is a really good learning opportunity. And now if we go in main CPP, we're going to see that this is going to become available. So we can build this with GCC again to bring Visual Studio Code up to date. And you see the build is good and our methods are usable even from derived classes. So for example, we can also set up an oval object. Let's say oval 1 and say draw. This is going to work. If we say oval 1, draw and pass in a parameter, let's put in 54, for example, this is going to do. You're going to see that this is going to be accepted by Visual Studio Code. And if we build and run this program, it is going to be calling the inherited functions in oval and circle here. The build is good. We can kill our terminal here and bring up a PowerShell window we can use to run our program. We're going to see that we call shape draw and shape draw because these are inherited functions from the shape class. That's why we are saying shape draw here. And we're going to be drawing our oval and drawing with a color depth. We're going to be drawing the circle and drawing with a color depth here. This is the message I want to convey. But the moment we override these methods in any downstream class, for example, if we go in our oval class and comment out the override for the draw method, notice that we are just overriding a single overload. Again, if we go back to our shape class, we have an overload that doesn't take any parameter. We also have an overload which is going to take one parameter. In oval, we are just going to override the overload that doesn't take any parameter. But this is going to hide all the other overloads we had for the draw method here. And this is the only overload that is going to be available in downstream classes. So if we go back in main, we're going to see that the one with a parameter is not going to work, and we're going to get a bunch of compiler errors. This is going to be the case even in circle. If we uncomment this guy, the others are going to be eclipsed. Again, the other one we have is just the one with one parameter, but this is going to stay true even if you have 100 overloads. All the others are not going to be available if you happen to only override one of the overloads. In other words, the other overloads are going to be hidden by this one override that you are putting in your inheritance hierarchy. You should really know this. If you want this guy to be available in downstream classes, for example, you can also override that in derived classes. This is an option. We can go in oval and put in another overload for this. This is going to bring this back in scope. So we can say oval draw here with the color depth. I don't think we copied the right thing. We can grab this and go in oval and put this in place. This is going to do. We're going to say oval drawing, and we can go in circle and also put this in. This is an option, and we're going to say circle drawing. And now you see that the squiggly lines in main go away because we have overridden all the overloads. Okay, if we build and run our program, we're going to see that this is going to work as we expect. The build is going to be good, and we can clear and run Rooster. We're going to see that overdraw called. We are calling our derived overrides, and this is really cool. This is what we want here. Let's take this back because we don't want these overridden in our inherited classes. So we're going to take this out in oval, and we're going to take this out in circle. And I want you to see that shape polymorphism is not going to work if you override your methods at a downstream level. So what we are going to do, we are going to go at the oval level and set up another overload for the draw method here. But this draw method is not going to participate in shape polymorphism because it is really declared at the oval level, and any base pointer we have or any shape pointer we have is not going to have any knowledge of this overload that we are about to set up here. This is what I want you to know. Okay, so we are going to go in our oval class and set up that overload. We can set that up here. It is going to be taking two parameters. One is going to be the color depth. The other is going to be the color. And we don't want to pass a string by a value like this. We can use std string view, and we can include that if we need to. But it looks like Visual Studio Code has got this from something else we have included before, but we can include that explicitly to avoid problems. So let's do that. We're going to say string view here. And now we want to see that this method is not going to participate in shape polymorphism, even if it is a virtual functions. The reason is, this is not going to be known by your shape pointers because it is not declared at the shape level here. I really want you to know this. We're going to take out everything we had here, and we can set up a shape pointer. We're going to say shape and say shape ptr, and we're going to set up a derived object here. We can say new and say circle. And what do we need to build a circle object? We need the radius and the description. So we're going to put that in place here. The radius is going to be something like 10. Why not? And the description is going to be circle 1. How creative. And we want to see if our method is available through polymorphism. And it is not going to be available because the method was not declared at the shape level. So if we do shape ptr and say draw, and we have a method which is going to take two parameters at the oval level. We have the color depth and the color. So for example, if we go in main and say the color depth is 45 0.2. Why not? Let's say this is something that makes sense, or let's use 45 because this is an integer parameter and we're going to pass in a string. Let's say red. You're going to see that this is not going to compile because the draw method with two parameters is not known at the shape level. This is the message I want to convey here. So if you want your method to be usable with polymorphism, the method has to show up at the top level. This is what I want you to see here. If we're trying to build this, we're going to get a compiler error, and you need to be aware of this. But note that even if this is not working with shape polymorphism, this can work with oval polymorphism. And this is an idea I am going to explore in the next lecture, where we learn about the fact that polymorphism can be set up at different levels. So we are going to stop here in this lecture and explore that idea in detail in the next lecture. So go ahead and finish up here and meet me there. In this lecture, we're going to explore the idea that we can do polymorphism at different levels in our inheritance hierarchy. Suppose we have a hierarchy like we see here. The top level class is animal, and we can derive from animal and create a feline animal. We can derive from feline and create a dog animal. We can derive from feline, create a cat animal. We can also do it the other way and create a bird, which is also an animal. A bird is going to have its own methods and member variables that make it a bird. We can derive from a bird, create a pigeon, and we can derive from a bird and create a crow. And we can do all these things that these animals do. So the idea I want to expose here is that polymorphism doesn't have to always only work on the top level class. If you have an inheritance hierarchy like this, if you want, you can declare a virtual method at the feline level and make sure that method is also available in deriving class, and you can set up feline polymorphism if that makes sense for your application. Following the same idea, you can also set up a virtual method in the bird class, and you can have that method overridden in downstream inheriting classes like pigeon and crow, and you can set up bird polymorphism in your C++ program if that makes sense. Of course, you can still use animal polymorphism if you want to do that, and that's going to work as well. This is the idea we're going to explore here. Okay, so with that inheritance hierarchy in mind, we can create animal polymorphism. And animal polymorphism is just going through the animal base pointer and using that to manage derived objects. For example, here we have a dog, we have a cat, we have a pigeon, we have a crow. We can do animal polymorphism and store in any kind of animal we have here. You see, we are putting in a dog, we are putting in a cat, we are putting in a pigeon, and we are putting in a crow. And if we do animal polymorphism and call the breathe method, which exists in any kind of animal we have in our program, this is going to call the most specific breathe method on each animal, and this is going to work really well. This is going to do animal polymorphism. Following the same idea, we can also do feline polymorphism, and in this case, feline is going to be acting as our base pointer. So again, we have our dog, we have our cat, we have our pigeon. If we do feline polymorphism, we will have to put in all kinds of crazy felines we have in our program. For example, we can put in dog and cat, and this is going to work. If you do feline polymorphism like we are doing here and put in an animal, this is not going to work because the animal top level class is probably not going to override the virtual method we are interested in here. For example, here we are calling the run method, and the run method is not set up at the animal level. Let's go back and look at our inheritance hierarchy here. You see, this is our animal class. Our virtual method is going to be breathe because any kind of animal we have is going to need to breathe. But the run method is set up at the feline level. So if we try and store in an animal in a setup that uses feline polymorphism, the run method is not going to be available and we're going to get a compiler error. So I want you to know this, but we will also see this in a minute when we hit Visual Studio Code to really play with us. Okay, we can also do bird polymorphism, and here you see we have two objects. One is a pigeon, the other is a crow, and we're going to do bird polymorphism here, and what that means is that we will use a bird pointer to manage all kinds of crazy birds in our C++ program. For example, we can use that to manage a pigeon, we can use that to manage a crow, and if we loop through our birds and call the fly method, the most specific fly method is going to be called. In this case, at the first iteration, we're going to call the fly method on our pigeon object. At the second iteration, we're going to call the fly method on our crow object here, and this is going to work. Now that you know this, we're going to head over to Visual Studio Code and play with this a little more. Here we are in our working folder. The current project is polymorphism at different levels. We're going to grab our template files. Let's grab it all. We're going to copy this and put this in our current project. And we're going to open this little guy in Visual Studio Code like we always do. And before we open this up, I am going to put in the classes I have lying around on my drive. And these are going to be the classes making up our inheritance hierarchy here to make things go faster. If you want, you can grab these classes from the attached resource section on this lecture. You're going to find all these files. You can download them and put them in your project and use that as a starting point. Because you don't really want to be creating all these classes, this is going to just waste your time. The basic idea I want to expose here is doing polymorphism at different levels. So we're going to open this up in Visual Studio Code by dragging and dropping here. This is going to give us our good starting point. You see we have a bunch of classes in here, but all these classes are really trying to set up the inheritance hierarchy we have here. The top class is going to be the animal class. We can derive from animal and create a feline class. And we can derive from animal and also create a bird class. We can derive from feline and create a dog. We can derive from feline and create a cat. And we can also derive from bird, create a pigeon. We can also derive from bird and create a crow class. And at each level, we're going to have a virtual method that we set up that other deriving classes can call through polymorphism. For example, if we do animal polymorphism, we will get the correct breathe method called regardless of the actual object we are managing with our animal pointer. If we do feline polymorphism, we can manage our objects through feline pointers, but we will get the correct run method called regardless of which kind of object we are calling this method on. So if we call the run method on a base pointer managing a dog object, we will get the run method called on the dog object. This is what we mean here. Okay, so we have our classes here. Let's take a closer look at our animal class. It is our top level class and it is going to have a virtual method which is called breathe. It is const because it is not modifying our class here. Notice that we don't have a virtual destructor because I wanted to keep this simple. But in your practical object, you should make your destructors virtual if you happen to have a virtual function in your class here. So for example, we can even do that. Let's make this virtual. This is not going to cost us anything. And this is going to be our top class. We can look at the implementation file. It is not going to do anything special. It is just going to forward whatever parameter we pass and use that to initialize our member variable. I think we can also go in and change our parameter to a string view. So we can do that, std string view. Let's go in the CPP file and also change that pretty quick. We're going to say std string view here. And this is our animal class. We're going to go in our feline class because that's the deriving class. Feline is going to be inheriting from animal publicly, just as we see here. We're not going to really do anything special. We're going to set up a member variable called firststyle, and we're going to forward the data from our constructor and use that to initialize stuff in our class here. Our parameters are also going to be passed as std string view types. So let's do that here. And this is in place. We also have a virtual method which is called run, and inside we are just printing which kind of object we have and giving a hint on the method that is being called here. This is what we just do here, and we don't intend to create feline objects directly. That's why we're not setting up any overrides of the top. That's why we are not setting up any direct specific overrides for these methods, but we will do that in downstream classes, for example, dog and cat, because that's going to make sense there. Let's go in the CPP file for feline and also change things a little bit. We're going to use std string view parameters. Let's do that for the second parameter as well. And this is our feline class. So we can go in and look at our dog class. Let's see if we can find it. And I don't think we made our destructor in feline virtual, so let's do that and look at our dog class pretty quick. Here we have our dog. It's going to have no member variable at all, and it will just forward this data to upstream classes. But we can override our breathe method we get from the animal class. We can do that, and we are going to say, we can grab this entire thing, and we're going to go in dog. We can do that if we want. We're going to put this method down below here, and we're going to say breathe. We're going to say that this is overriding what we have on top, and we're going to say dog breathe cold. This is going to do, and we also need to change our parameters to std string view. Let's do that. This is going to make things work better because we will avoid unnecessary copies, and we will be able to pass string literals as parameters to this constructor here. This is what we want to achieve with this. We can hit the CPP file for our dog class, and we're going to change the parameters again, std string view, and we're going to say std string view as well here. And we're going to go to the header file again and make sure we have a virtual destructor here, because this is good practice if you are using virtual functions like we are doing here. We can grab our breathe method and hop over to our cat class. Again, remember the inheritance hierarchy we are going after is what we have here. So if you are confused, please come back and look at this. You're going to really understand what we are doing here. We're going to go to the dog class and make sure it is working as we want. So we just did the dog class, and we just made sure it works like we want. Now we're going to hop over to cat and make sure it is. Now we're going to hop over to the cat class and make sure it is overriding the breathe method to make sure the correct method is called. Okay, so let's do that. We're going to hop over to our cat class. It is going to have its own meow method, but it can also override the breathe method we get from the animal class. So let's do that. We can grab this and we can go to our cat class. Let's do that. We're going to put in our virtual method, and we're going to say cat breathe, and this is really all. We also need to set up our parameters correctly using std string view. Let's do this, std string view, and this is really all we need to do here. We can also make our destructor virtual because this is good practice. We hop over in the CPP file and change our parameters to be of type std string view. Let's do this. And this is done. We can really work with this inheritance hierarchy here. We're going to also go pretty fast and work on the other side of our inheritance hierarchy. We're going to work on birds. Let's look at the bird class. It is going to inherit from animal. It is not going to do anything special really, but we just want to change the type of our parameters to std string view. And we're going to do that on the second parameter. And we are going to hop over in the CPP file and change these things here. Let's do that. We're going to say std string view and do the same thing here, std string view, and bird is done. We can grab our breathe method. For example, let's go back to the top and grab that from our animal class. And we're going to hop over to one kind of bird we have in our program. We can look at pigeon, for example, the last class here. We're going to override the breathe method, and we're going to say pigeon breathe, and we are going to change the type of our parameters here to std string view, and we're going to do the same here. And let's hop over to the CPP file and change the type of our parameter. Let's do that for the second parameter here. This is done. Let's look at the second kind of bird we have. I think we have the crow class. We also want to override the breathe method. We're going to say crow breathe, and we can go up and change our parameter to be of type std string view, and we're going to do that here. Again, if you are not interested in these changes, you can just grab the code and you're going to have all these classes ready for use. I just wanted to correct this little problem I had in my classes on my drive, because this is not good design in modern C++. We want to do things proper because we are really learning about modern C++ here. Let's hop over to the CPP file and finish this up. We're going to change the type to std string view, and let's do view correctly. And we're going to say std string view on the second parameter, and this is done. Now we have our inheritance hierarchy, and we're going to start by looking at animal polymorphism. Again, we just set up this inheritance hierarchy. Now we are going to try and do animal polymorphism. Okay, so now we're going to hop over to the main CPP file, and we are going to clean it up a little bit, remove whatever it is we don't need. We are going to put in our includes. We're going to include all of the things in our file here: animal, feline, dog, cat, bird, pigeon, and crow. We're going to include all this. And we just want to play with animal polymorphism here. We are going to set up a bunch of objects, and we're going to put in dog, cat, pigeon, and crow, all kinds of crazy animals we can create in our C++ program. And we're going to put them in an array that is storing animal pointer. And this animal pointer is going to enable polymorphism for our objects that we have in here. Remember, animal sets up a virtual method called draw. If we go back, we're going to find that. And we made sure to override this method in all kinds of crazy animals we can create. For example, in our cat, we have a breathe method overridden. In our dog class, we have the breathe method overridden. And what we want to achieve in our main CPP file, let's go there if I can find it. We want to achieve a setup so that if we call the breathe method, we're going to call the most specific breathe method on our animal pointer here, even if we are calling that method on a base pointer. This is what we want to achieve. And this is going to be animal polymorphism because the base pointer is of animal type. This is what we mean here. Let's try and build this program. So if we loop and call the breathe method, the correct breathe method is going to be called. And what we expect for the first object, which is a dog object, we're going to get the dog breathe method called. For the second iteration, the cat breathe method is going to be called. For the third iteration, the pigeon breathe method is going to be called. For the last iteration, the crow breathe method is going to be called. This is what we expect to see if we run this program here. So let's do this. We're going to pass this through GCC, our favorite compiler. We can use any compiler we want, but GCC is going to do in this case. Okay, the build is good. We can bring up a PowerShell window to play with, and we're going to run Rooster, our program. And if we run this, you're going to see that in our loop, the first iteration is going to call dog breathe because the first object is a dog. The second iteration is going to call cat breathe because the second object is a cat. The third iteration is going to call pigeon breathe because the third object is a pigeon. And the last iteration is going to call crow breathe because the last object is a crow. And notice that we are calling the breathe method through a base animal pointer. And this is what polymorphism is all about. And what we are doing here is animal polymorphism. But this is not what we are really after in this lecture. We want to see that we can also do feline and bird polymorphism in our inheritance hierarchy. So we're going to put in a separator. Let's do stdc out and put in a bunch of dashes here, or hyphens. Some people call them like that. Doesn't really matter. And we're going to play with feline polymorphism. Let's do this. We are going to go down and put in a simple piece of code that we're going to be using to play with things here. And we're going to set up a bunch of objects. We have a dog, we have a cat, we have a pigeon. And we are going to use a feline pointer to manage feline-derived objects. For example, we're going to use this pointer to manage a dog and a cat. But one thing I want you to see is that if you put in a pigeon, for example, this is not going to work because a pigeon is not a feline. So the compiler is going to give you a compiler error. Let's try and do that. We're going to try and put in pigeon here, pigeon 2. You can select this. And if we do that, you're going to see that we get a squiggly line. This is a sign that this is going to go wrong because we are storing in felines and the pigeon is really not a feline even by our inheritance hierarchy. So the compiler is going to give us a compiler error. Let's try and build to show you the compiler error. Okay, the build finished with errors, and if we go in, we're going to find that cannot convert pigeon to feline pointer. So this is the error here. You can't do something like this. Even if you create an animal object, let's say that we're going to go in and create animal, and we're going to say animal1. We can do that. And we're going to pass in the description. I think we can do that. We can do something like this. And if we try and pass in the address of animal1, let's do that. This is also going to give us a compiler error because animal is not a feline. Again, if you get confused, come back and look at our inheritance hierarchy here. What we are setting up in our code, we are using feline polymorphism, but we want to store an animal in an array that is storing felines. And this is going to be a problem because the compiler isn't really going to be able to process this. Our base pointer is a feline, and we should really be able to only store in derived types from feline. But we are putting in a superclass or a parent class of feline, which will not be able to have the specializations that feline is doing. So the compiler is really saying, this is crazy, I can't do this, I am going to throw a compiler error. This is the behavior we get here. Okay, so this is going to give us a compiler error, and let's run and see that. We're going to use GCC. The build is going to finish with an error, and we are going to see that we have an invalid conversion from animal pointer to feline pointer. And this is what we want to do here. We want to convert an animal pointer and store that in a slot that is only supposed to store feline pointers. So this is not going to work. But if you do everything right and only put in derived types of feline, you're going to get the correct thing to work. And let's look at our dog class. Let's open it again. We're going to look at dog, and we're going to have a run method, but we don't have that set up for our dog class, but we can do that pretty quick. Let's look at cat and see if we have a run method. We don't, but we can set that up. Let's go to feline and copy our virtual function. We can do that. And we are going to go in dog and set up another virtual method, which is going to be run. And this is going to be an override of what we have in our inheritance hierarchy. So this is an override method. We are also going to do the same, but before we go, let's say that this is the dog class we are doing things from. We are going to grab this method again and go in cat, because that's another feline we have in our program. We can do something like this, and we're going to say cat here. Okay, so now let's come back to main, and we're going to build again. We're going to pass this through GCC, and we still have a pigeon in here, so this is not good. Let's take this out and make sure that we only have felines in this array here. Let's build again. Okay, you see the build is good. We can clear and run rooster. We're going to have our separator here, and you're going to see that we are calling our dog method at the first iteration because the first object is a dog, and we are calling a cat running method because the second object is a cat, and this is feline polymorphism in action. Hopefully this proves to you that we can do polymorphism at different levels depending on what we want to achieve in our C++ program. To close off this lecture, we are also going to set up bird polymorphism. Let's do that. We're going to put in a separator, and we're going to say bird polymorphism. And we are going to put in a bunch of objects and set up a base pointer array, which is going to be a bird pointer array in this case. And we're going to be storing in derived objects of the base pointer type. So we are going to be storing in derived objects of bird, and we have a pigeon and a crow, and this is the setup we want here. Now, let's go and look at the setup we have in our pigeon. For example, we don't have a fly method, we just have a coo method because a pigeon coos If we go in our crow, we're going to see that we don't have fly method. We just have in the cow method because a crow cows. But if we call our fly method, because we don't have this method overridden in any downstream classes of bird, we will get the base version of the fly method called. So we will get this method here called. I want you to see this. Let's hop over to the main CPP file and make sure we have the correct setup. Looks like this is what we want. We're going to build this with GCC. The build is going to be good, as we see here, and we're going to run. Now we're going to see bird fly for pigeon 1 and crow 1, but this is not using any derived method that we have in our crow and pigeon class. If you want, you can also override the fly method and you're going to get that called. Let's actually do that because I like to show you things directly so that you can really see with your own eyes. So we're going to go in bird and grab the fly method, and we're going to override this in pigeon. We can do that, and we're going to override here, and we are going to say pigeon here, and we can grab this and put this method also in the crow class. We can do that, and we're going to say crow here. Now if we run this program using what we have in the main CPP file, for the first iteration we're going to call the fly method on the pigeon object because we have the fly method overridden at the pigeon level. As we see here, this is right here beneath our eyes, and we're going to see this in action if we run this program here. The same is going to happen for the crow object here. Let's build with GCC to really prove this. The build is going to go through, we can clear and run rooster, and we're going to see pigeon fly, crow fly. This is proving what we set up in this lecture here. This is really all I had to share. I hope you found this interesting. The main message is that you can set up polymorphism at different levels in your inheritance hierarchy, depending on what you want to achieve in your C++ program. We saw that we could do the usual thing and use the top level class as the driver for our polymorphism, and we did animal polymorphism here, but nothing prevents you from doing feline polymorphism or bird polymorphism as we saw in this lecture. We are going to stop here in this one. In the next one, we're going to see how we can do polymorphism with static members. Go ahead and finish up here and meet me there. In this lecture, we're going to explore how inheritance and polymorphism play out with static members that we have in our classes. And we're going to be using this inheritance hierarchy here. Our base class is going to be shape. We're going to inherit from that and create an ellipse class. Let's look at some code here. So we're going to set up our base class as shape, as we said, and we're going to have one member variable, which is going to be our description here. We're going to have a constructor and a destructor, and we're going to have a default constructor, which is really not important here. But notice that we have a static member, which is called mCount. And if you remember, a static member variable is a kind of variable which is associated with the type itself. It's not associated with any object that you create. If you forgot this, please go back to our chapter on classes or user-defined types. You're going to learn all about static variables. Here we are just exploring how they play out with inheritance and polymorphism. Now we have a shape class. If we inherit from it and create an ellipse class, for example, we're going to have all the data that was public in our base class to be public in this class as well. So by that logic, we are also going to get this static variable inherited, and we're going to be able to access it from ellipse objects. Let's try and use this in code here to really drive the point home. Here we are creating a bunch of shape objects. Here is our first shape. We print our static variable through this syntax here because it is public. We can do this. We're going to get a 1 because we just have one shape here. We create a second shape and we print the count. We're going to get 2 because we just have 2 shapes in here. We create our third shape and we try and print the count. We're going to get 3. And if you wonder how we are incrementing this static variable, we may do this in our constructor. We're going to see how this works exactly once we hit Visual Studio Code in a minute. But note that every time we create an object, we're going to be incrementing our static variable. That's why we see 1, 2, 3 as we create these objects here. This is the logic. Now, we have three shapes here. We go down and create a new object, which is of ellipse type. If we print the shape count, we're going to get 4 because an ellipse is a shape, and ellipse is inheriting the static variable from shape. So we're going to get a 4 printed out here. But if we also print ellipse count, we're going to get a 4, even if we really just have one ellipse. So the static variable from shape is being inherited and used in our ellipse class, and this may not be what we want. So the problem here is that the static variable we are using in shape and ellipse are the same because the one we have in ellipse was inherited from shape. That's why we have these results here. But sometimes we just want to have ellipse count to be 1 here because in reality we really have one ellipse. So how do we do that? To get that behavior, you can also set up another static variable named exactly the same way at the ellipse level, and you can do that like this. You can also override the getCount method to return the current count in ellipse. This is going to work through polymorphism because the getCount method is a virtual function. If you call this method through a base pointer, you will get the correct one called, which is going to be the most specific one through polymorphism. But what we want to see is how things are going to work now that we have a static variable which is named exactly the same as the one we have in our base class here. The one in shape is exactly named mCount. It is a static variable of type int. The one we have in ellipse is also the same. It is a static variable called mCount of type int. But now ellipse is going to maintain its own static variable and shape is going to maintain its own static variable. Now we are going to get this kind of behavior. We are going to see that if we try and print the count of shapes we have, we're going to get a 4 here. But now if we try and print the count from ellipse, we're going to get a 1 because we really have one ellipse. And this is working because ellipse is going to maintain its own static variable, and this is going to give you this behavior if it is what we are after in our C++ program. Now we can also go on and create a bunch of other objects here. We are going to store them in this array, which is going to be storing shared pointers to shape, and we're going to store in derived objects. This is the syntax we can use to do this. And the moment we do this, we're going to get 6 shapes because in total we really have 6 shapes, but 3 of those shapes are going to be ellipses. And if we try to print the ellipse count, we're going to see that we have 3 ellipses in our C++ program, and this is going to do what we want. Another thing you could do is also do shape polymorphism and call the getCount method, and you're going to get the correct getCount method and print the most specific count. If we are calling that method on an ellipse object, for example, we're going to print 3. If we call that on a shape object, we're going to get 6, and that's the behavior we could achieve with polymorphism with static member variables, and I really want you to be aware of this. Now that you know this, we're going to head over to Visual Studio Code and play with this a little more. Here we are in our working folder. The current project is Inheritance and Polymorphism with Static Members. We're going to grab our template files and put them in place. And I am going to grab our classes from my drive and use these as the starting point. Again, if you don't want to type or create these classes, you can use the files provided in the resource section of this lecture. You can download them and use them directly without having to create them, because we are really interested in how static members behave with our inheritance hierarchy, which happens to be setting up polymorphism. This is what we want to learn about here. I am going to open this up in Visual Studio Code, and we're going to take a good look at our classes. The base class is going to be shape, which is what we have here. It's going to have a virtual method, which is getCount here, and we have a static member, which is of type int. I am going to change my parameter here to be std_string_view, because that's what we should do in modern C++. Let's look at the CPP file for this, and we're going to fix this a little bit. And we're going to hop over back to the header file and look at what we have. We have a virtual method, which is going to return this count here. It is a const method because it's really not going to modify. It's just going to return a copy of the count member variable we have here. And this is a static member variable. Notice that it is not in line. So we will need to define this in the CPP file somewhere, because this is a declaration. We need to put in a definition, which is what we have in our CPP file here, because we are doing things in the older C++ way. We are going to increment our count member variable in our constructor, and this is going to achieve the behavior we really want, to have the mCount member variable, which is static, incremented each time we create a shape object here. Let's go back and look at our destructor and make sure that it is virtual, because we have virtual functions in this class, and this is the setup we have. Let's look at ellipse, and we're going to take out this static member variable because we don't want to set it up as of now. We will enable it in a minute. Let's make sure we remove this, and let's remove this because I don't want this. And now we can try to create objects of our classes and see how these guys play out. We can also go in ellipse and make sure the constructor is taking std string views where we are needing strings. We can do that and hop over to the CPP file and do that, std string view. I think this is going to make Visual Studio Code happy by now. We can hop over to the main CPP file and clean it up a little bit. And we are going to include ellipse. And in our main function, we're going to create a bunch of objects. Let's close the left sidebar here because we don't really need that anymore. We're going to create a shape object and we're going to print the shape count. We expect to get a 1 because we just have one shape at this moment. We're going to create a second shape here. And if we print the count, we're going to get 2 because we have 2 shapes. This is what we expect. We create another shape, which is going to be shape 3 here. We print the count, we're going to get a 3. But the problem is going to come when we create an ellipse here. If we create an ellipse and print the count, we're going to get a 4 because we have 4 shapes in our C++ program. But if we print the ellipse count here, we expect to get a 1, but that's not what we're going to get. We're going to get a 4 because the mCount variable in ellipse is inherited from our shape class. So it is going to be the same thing we have in shape here, because if you go back, you're going to see that at this point, ellipse doesn't have a static variable mCount of its own, so it's going to use the one it is inheriting from the shape class. This is the behavior we're going to get here, and I want you to be aware of this. If this is what you want, this is fine, but in most cases, you will want this to be different because you want very clear information about how many objects of each type you have created in your C++ program. If it is just shape, this is going to be really vague because you want to know if it is an ellipse, if it is a rectangle, if it is a triangle. This is not going to be super clear. So let's build and really show you the problem here. We're going to pass this through GCC, our favorite compiler. We can also bring up the left sidebar, no problem here. And we're going to bring up a terminal window or a PowerShell window, I can say. We're going to clear and run Rooster. You're going to see that the shape count is going to be 1, 2, 3, and we have a 5 here because we are also incrementing the mCount variable in our derived class. So we are incrementing twice if we create an ellipse object. Let's show you this. In ellipse CPP, we are incrementing the mCount member variable, but in the base class, we are also incrementing that. In the CPP file, that's what we have here. And notice that the derived class is also calling the base class through our initializer list here. So this is the behavior we have. We shouldn't be incrementing this because ellipse doesn't have its own static variable as of now. Now we're going to build and really solve this problem. Now you see the kinds of problems you can run into if you have a static variable that is named exactly the same way and you have an inheritance hierarchy. Really weird problems can pop up and you need to be aware of this. Let's build and see that the problem actually disappeared. Okay, the build is good, we can clear and run Rooster. We're going to see that now this is what we expect. 1, 2, 3, because we have 3 shapes created up to this point here. If we create an ellipse, that's going to be another shape. If we get the shape count, we're going to get a 4. But ellipse count is also giving us a 4 because ellipse doesn't have its own static variable. To solve this problem, we can go to ellipse and set up our own member variable at the ellipse level. So we can enable this and uncomment it. We're going to go to the CPP file and make sure we are incrementing to get the correct count incremented here. I think this is all we need to do. We are also going to initialize the static variable we have at the ellipse level. This is going to do what we want, and we can build again. Now, we're going to get the behavior we want, because at this point, we are going to print a 1 for the ellipse count. And this really makes sense because we have 1 ellipse, even if we have 4 shapes in total. So this is the design I think makes more sense in our C++ program here. We are going to build this again and pass this through GCC. The build is going to be good. We can clear and run Rooster. Now we're going to see that we have 4 shapes and 1 ellipse. And this is what we want. Now that we have this, we can really do all kinds of crazy things. Hopefully you can see that the static variable is working exactly as we want. We can print the ellipse count, we can print the shape count if that's what we want in our C++ program. But we can also do shape polymorphism and get the correct getCount method called in our C++ program. For example, if we call the getCount method on a base pointer that is managing a shape, we're going to get this one called. If we have a base pointer that is managing an ellipse, we're going to get this one called. This is going to be super cool. Let's go up in our program and set this up. We're going to do this on the fly. Let's say shape polymorphism, and we're going to say shape pointer, and it is going to be an array. Let's say shapes. This is going to do, and it is going to be just an array. And we're going to initialize this and store in a bunch of objects. Let's put in our closing brace here. Let's go up and see what we have. For example, we have shape 1 and ellipse 1. We can use these. We're going to put in the address of shape 1 and we're going to put in the address of ellipse 1. This is going to do. And we can loop through these guys and call the getCount method. So let's do this. We're going to say for auto s. And let's do a reference because we don't want copies. And we're going to say in shapes. And we're going to call the getCount method. We're going to say s and say getCount. This is going to give us the count. And we can print this out if we want. We can say stdc out and count. And we're going to put a new line character here to separate these guys. And we can put a separator here. We can copy what we just used in our C++ program here, just to make sure this is super clear when we print things on the terminal here. We're going to build our program and see if it actually works. The build is going to be good. We can clear and run Rooster. We're going to see that the count is going to be 4 for the first iteration because we're going to be calling the getCount method from shape because that's our base pointer. So this is what we're going to get. We're going to print the mCount member variable from the base class. That's why we have a 4. But on the second iteration, the object is ellipse, and we are using polymorphism because we are going through a base pointer, and this base pointer happens to support the virtual method getCount. We will get the most specific one called on the current object that our base pointer is managing here, and this happens to be an ellipse. So we're going to call the ellipse version of our virtual function here, and we will get a 1 because we really have 1 ellipse in our C++ program. This is what we see here. This is really all I wanted you to see in this lecture, how you can use static member variables with inheritance and polymorphism. And you need to be aware of these little things that can really be confusing, especially for beginners. We are going to stop here in this lecture. In the next one, we're going to learn about the final specification we can use in our inheritance hierarchy. Go ahead and finish up here and meet me there. Go ahead and finish up here and meet me there. In this lecture, we're going to learn about the final specifier used in inheritance hierarchies. This is going to allow you to do one of two things. You will either be able to restrict how you override methods in derived classes, or you can restrict how you can derive from base classes. I know this is in the air, but we're going to look at a few examples to really drive this home. Suppose we have an inheritance hierarchy like we see here. The top class is animal. We can derive from this and have feline. We can have bird as a derived class. Feline can be inherited to have dog and cat. And you can derive from cat, for example, to have wildcat and bulldog from dog. You can do all these things here, and this is inheritance hierarchy we're going to be using to learn about these things. Now, here is a possible implementation for the dog class, which is going to be inheriting from feline publicly, as we see here. But take a look at the run method we are setting up in dog. We are appending a final specifier, and what this is going to mean is that no downstream inheriting class will be able to override the run method further. This is what we can achieve. So if we don't want our derived classes to override our virtual method, we can mark that method as final in our class. And we are basically saying, I am going to put in my implementation, but I don't want any deriving downstream class to override this method further. If they do that, they are going to get a compiler error. And this is something we can achieve using the final specifier in our inheritance hierarchy. Again, in this case, we are using this to restrict how people can override our own virtual method in downstream classes. Or I shouldn't really say our own method because it may be coming from upstream, but you are restricting people from overriding that method further in downstream classes here. Okay, so this is the first use we have for the final specifier. But we can also restrict people from inheriting altogether. So here we have a simple example to drive this home. We have our cat class. It is going to be inheriting from feline, but we are marking our cat class as final. And what this is going to mean, if anybody tries to inherit or derive from cat in any way, they are going to get a compiler error, and this is what we can achieve with the final specifier. Again, there are two things. You can restrict how people override your virtual methods. If you want to restrict that from the current class, you can mark your virtual method as final. You can also restrict how people inherit altogether from your class, and if you want that behavior, you can mark your class as final using the syntax we just saw in the slides here. Okay, now that you know these things, let's look at a few things that may be interesting. For example, here is a simple fact that you can create a class right away and mark it as final. And when you do this, nobody will be able to ever inherit from this class in your program. And if we do this, we will get a compiler error, for example. This is one thing I find interesting, and I really wanted you to know this. Another thing is that it is possible to introduce useless virtual methods in your inheritance hierarchy. For example, if our cat class is marked as final, what this means is that nobody will ever be able to inherit from this class. But we are going further and setting up a virtual method which is meant to be inherited or overridden in downstream classes. But how do we get a downstream class if we can't inherit from the cat class which is marked final? So we have conflicting ideas here. On one hand, we are saying we can never inherit from this cat class. But on the other hand, we are setting up a method that is meant to be used or specialized in derived classes. So this is something that is interesting. This code is going to compile, and I think maybe in future standards of C++, they are going to fix this problem and maybe give you a compiler error if you try to do something like this. But at this point, you're not going to get a compiler error. This is just going to be valid C++ syntax. Even if this is really weird, we have conflicting ideas here. Okay, one thing you should know though is that we can override in a final class. And this is going to make sense because, for example, the run method is coming from the feline class. And here we are just specializing that. So we are marking that as an override here, even if this is a final class. So be careful. This is valid C++ syntax. This is going to work just fine. Another thing you can do, which is pretty useless in your C++ program, is to introduce a virtual method and mark it as final right away. So again, this is really weird. We have two ideas that are conflicting. The virtual keyword means that we want this to be specialized in downstream classes. But again, we are saying this method is final. So no downstream class will override this. If they try to do that, they are going to get a compiler error. So this is, again, a bunch of conflicting ideas. C++ is going to allow this syntax. This is not going to give you a compiler error, but this is weird, and you need to be aware of this. Okay, now that you know these ideas, we're going to head over to Visual Studio Code and play with the final specifier in our inheritance hierarchy. We will be setting up this kind of inheritance hierarchy, and we will set up a bunch of virtual methods and mark them as final. I think we will do that in the dog class, and we will mark a bunch of classes as final and see that if we inherit from them, we're going to get a bunch of compiler errors. So let's do this. Here we are in our working folder. The current project is final, and we are going to bring in our template files pretty quick. We're going to use this as our starting point. We're going to put that in place, and I am going to put in a bunch of classes I have lying around on my system because I don't want to set up these classes. That would be a waste of your time. Just know that we are trying to set up this kind of inheritance hierarchy. Animal is going to be our top dog, or animal is going to be our top class, and we will be inheriting from this, creating an inheritance hierarchy we can play with in our code here. Okay, so we are going to open this up in Visual Studio Code. So let's do that by dragging and dropping here. This is going to give us all these crazy classes we have. The top class is going to be animal, and it is going to be defining the features any kind of animal we support in our C++ program is going to have. For example, any kind of animal will need to breathe, and we will set up this virtual method here. And we will be inheriting from this animal class to create a feline class and a bird class. This is something we did in a few previous lectures, and we are just reusing this inheritance hierarchy here. Let's look at the feline class. The feline class is going to set up a virtual method which is called run, and the method is going to be overridden in the dog. For example, we can override the run method, but notice that we are marking that as final. Okay, so look at this. The method is final, and what this means is that no downstream classes inheriting from dog will ever be able to specialize or override this method further. If they try to do that, they will get a compiler error. Notice that this may be our method, or it may be a method coming from upstream classes. In this case, the run method was introduced at the feline level. You see it was introduced here, and dog happens to be overriding this method here. That's why we have the override keyword, but at the same time, we are going to mark it as final and prohibit or prevent downstream classes from overriding this method further. If we look at our bulldog class, we're going to find the class to inherit from dog. We have our run method here. It is commented out at this moment. I just want you to see that our code is just going to compile. If we compile it now, let's do this. We're going to pass this through GCC. Okay, you see the bold is good, and we have generated our binary, which is really not doing anything because our main function is just some dummy code we have here to make sure it works with C++20. But what I want you to see is that if you go in Bulldog, let's go in our Bulldog class and uncomment this class here, or this virtual method, we're going to see that we're going to get a compiler error. We have a squiggly line, meaning that we did something wrong. And let's look at the problems tab from Visual Studio Code here. Cannot override final function dog run. This is a final method from the dog class. If we try to override it further, we will get a compiler error. This is something we can achieve by marking our virtual method as final, as we are doing here. Now, if we try to build this program, we're going to get a compiler error. Let's pass this through GCC and let you see this. Okay, you see we get a compiler error, and the error is that we are overriding. Let's go up and see the error here. Error, and on line 12 in Bulldog H, we see that we are overriding a final method. Virtual void bulldog is a final function, and we are overriding this, and this is going to give us a compiler error. This is the behavior we get. So the message here is that you can go in your inheritance hierarchy at any level and mark a virtual method as final and prevent downstream classes from specializing or overriding that method further. And if they do that, they will get a compiler error. This is something we can achieve in our C++ program. Another thing you can do with the final specifier is that you can prevent people from inheriting from your class altogether. Let's go to our cat class. I think that's the example that sets that up. We have a cat class. It is going to be inheriting from feline, but the class is marked as final. Now, what this is going to do, it's going to throw a compiler error anytime somebody tries to derive or inherit from this class here. So if somebody tries to inherit from cat, as we are doing here, create a wildcat from a cat, we are going to get a compiler error because we can't inherit from cat altogether. It is a final class at this moment. Okay, so let's look at our wildcat class. It is going to try and derive from cat. We can do something like this. We can remove our comments here. And if we try to do this, we will get a compiler error. Let's look at the CPP file and see what we have. It has nothing special. But if we try to do that and inherit from cat, we will get a compiler error because the cat class is final and you cannot derive from it. If you do that, you will get a compiler error because the cat class is final. This is what I want you to see here. Let's try and build our program again. We're going to pass this through GCC and we will see our compiler error. Okay, the build is finished with errors. If we go up, we will see that we cannot derive from a final base class. If we do that, we will get a compiler error. And this is what I want you to see here. Okay, now that we know this, we're going to take this back and take out the compiler error here because we want our code to compile. We're going to make sure it is compiling fine. Okay, now the code is compiling because we are no longer trying to inherit from cat. And I want you to now see a few interesting facts about the final specifier when it works together with virtual functions. Let's go to the main CPP file and show you the first fact. And that's that you can create a class right away and mark that as final as you create it, as we do here. If you do that, this class is going to not be inheritable. And if you try to inherit from it, you will get a compiler error. Let's take out everything we have here and just say hello in our main function. This is going to do just to have something. This is going to give us a compiler error because we can't inherit from a final class. Let's build and show you the compiler error. This is going to go through GCC and the build is going to finish with errors. And we have our message here. And we don't have the error we expected because we forgot to put our closing semicolon